Professor, some methanol leaked, and the alarm on the toluene detector went off. Why did the alarm go off detecting methanol and not toluene? Is it even possible for the alarm to go off if a gas other than the detection gas is present in the first place?
Yes, a gas detector can respond to something other than the detection gas. In cases like that where, for unintentional factors, the gas detector's alarm sounds or the value indicated changes, we call that interference. Also, when assessing interference, a sensitivity curve and data known as interference data are extremely useful. We'll start by learning about interference. When a gas other than the detection gas comes into contact with a gas detector, depending on the type of gas, it may have an effect on the gas detector's indication values. We call these gases interference gases.
I see. Can you give an example of the kinds of interference there can be with gases?
For instance, there can be interference with catalytic combustion method sensors, which are used to detect combustible gases. Catalytic combustion method sensors detect gases by igniting gas through a catalytic combustion reaction on its internal components. In other words, catalytic combustion method sensors are sensitive to all flammable, or combustible, gases. On the other hand, they are not sensitive to non-combustible gases, or gases that don't burn. Interference doesn't always have to be a weakness. Depending on how the sensor is used, it can be a good thing. With combustible gases, if a combustible method sensor is sensitive to them, then you can detect all combustible gases with a single sensor, so interference is useful in situations where the purpose of the sensor is to prevent explosions in the workplace. Next, let's take a look at sensitivity curves and interference data, which tell us how sensitive a sensor is when detecting gases other than the ones it is meant to detect. First, let's look at sensitivity curves. This sensitivity curve shows the sensitivity of a catalytic combustion method sensor when detecting an interference gas versus a detection gas. In the case of this sensitivity curve, the sensor sensitivity at 25% LEL isobutane is the same as the sensitivity at 21% LEL methanol.
Oh, so that tells us that when we want to use the catalytic combustion method sensor to detect isobutane, methanol will interfere greatly.
Now, let's look at interference data. This interference data is a table of interference gases for a detection gas when using a potentiostatic electrolysis method sensor. The red box in this interference data shows that when the potentiostatic electrolysis method sensor, which is designed for ammonia, comes into contact with a 1.01% concentration of isopropyl alcohol, the indication value will display 0.8 ppm.
So, written in each row in the table, going across, is the name of the interference gas, its chemical formula, its concentration when it hits the sensor, and the value that is indicated when in contact. So, Professor, my understanding is that the sensitivity curve and interference data are both used to see how much interference a gas is causing. But are there times when you would use either the sensitivity curve or interference data over the other based on the gas sensor's working principle?
Coherence will show up either in the sensitivity curve or the interference data, and that is determined based on the sensor's working principle. There can be many factors that contribute to this, such as changes or no changes in the point when the alarm sounds or a different sensor output curve for every sensor. Working principles for sensors that are suitable for sensitivity curves are catalytic combustion, semiconductor, infrared, thermal conductivity, and hot wire type semiconductor. And principles suitable for interference data are potentiostatic electrolysis, tape, light wave interference, and pyrolysis particle detection. It's a good idea to know which working principles are applicable to sensitivity curves and which are applicable to interference data.
Okay, I got it.